In this video, we're going to look at several examples of using our derivative shortcut rules that we have derived to finding the formula for the derivative, the first derivative function, given the formula of the original function. So let's just recall real quickly some of our rules. These are the rules that we're using. These are the rules that we use in a calculus class that does not have a trigonometry prerequisite like a survey of calculus class. So below f, g, u, and v are functions of x, and b, c, and n are constants. The derivative of a sum is the sum of the derivatives. Derivative of f of x plus g of x is f prime plus g of prime. The derivative of a constant times a function is a constant times the derivative of the function. The derivative product of two functions, f times g, is f times g prime plus g times f prime. Or if you had three or more functions multiplied together and to find the derivative of that product, it's the derivative of the first factor times the others, plus the derivative of the second times the others, plus the derivative of the third times the others, and so forth until you run out of factors. This is a formal notation for that sum. The quotient rule says the derivative of an f of x over g of x is g times f prime of x minus f times g prime of x over g of x squared. And I like to think of this chain rule really in this last version here. The derivative of f of u, where you've done a substitution where u is some function of x, is f prime of u, that is the derivative of f as a function of u, with u plugged in, but then you take the derivative of the u. The derivative of an inverse function is 1 over f prime evaluated at f inverse of x. So far, the main reason we've used this one is really just to find the logarithm rule. And later on, we can use this for those going on to Calculus 1. We can use this with inverse trig functions to help find their derivatives. The derivative of a constant is 0. Derivative of a constant function. The derivative of u to the n, where n is a constant, is n times u to the n minus 1 times the derivative of the u. The derivative of log of u of absolute value is 1 over u times du over dx. The derivative of log of u without the absolute value is still 1 over u times du over dx, but we have to put the restriction that u has to be positive. The derivative of b to the u is ln of b times b to the u times the derivative of the u. And a special case of that, when b is e to the u times du over dx. And the generalized power exponential rule says the derivative of u to the v, where u and v are both functions of x, is the power rule plus the exponential rule. So that is v times u to the power of v minus 1 times du over dx, plus ln of u times u to the v times dv over dx. So with these rules, we can find the derivative formula for any formula we're given that's built up out of addition, subtraction, multiplication, division, powers, roots, logarithms, exponentials, any of those things that are built up together, we can find the derivative. Now the key to understanding which rule to use first is to understand the structure of the function. So imagine you were to plug in a specific value for the input x. Think through the steps of evaluating the function and determine the last step. In other words, the outermost function, the outermost link in the chain of operations. So then, if you have to, make an appropriate substitution, but you can apply the derivative shortcut rule that corresponds to that last step. So here are a series of exercises. There are 10 of them here. And take these 10 exercises and let's see, oops, there needs to be a change in this last one. Take this, and each of these, what I'd like you to do is to find the first derivative, find the formula for the first derivative. And while you're at it, then go ahead and use your scientific graphing calculator to check your answer. We've already seen how to do that. You let y1 be the original function, let y2 be the numerical derivative of y1, and you let y3 be the formula you come up with for your answer for the derivative formula, derivative function. And so when you do that, the y2 and y3 should match in the graph and in the table. So take a look at the table and make sure they match. And then use your graphing calculator to graph both the original function and the derivative, and make sure that the characteristics that you see are the ones that they need to be. So I'm going to let you take these, work through these yourself, and then come back and we'll check these as this video goes on. Press pause, write these down. After you work them out, come back and pick up the video at that point. Press pause now. Alright, on the next example, on the first example here, okay, we have, let's see, f of x equals 5x cubed minus 3x squared minus 7x plus 4. Well, this kind is pretty easy to take the derivative of. We take the derivative of the first term by just, well, first of all, it's a sum, so you take the derivative of each term. And then within that, we use really a combination of the constant multiple rule and the power rule, but you could do it all in your head pretty easily. You take the 3 times the 5 is 15, subtract 1 from the power is 2. 2 times negative 3 is negative 6, subtract 1 from the power goes down to power 1. 1 times negative 7 is negative 7, and the x goes away, or the derivative of x times a constant is that constant, and the derivative of a constant function, the 4 part here, that derivative is 0. So we could check that, to make sure we did it correctly, by using this method. Type the original function in here. Here I use the newer operating system on a TI-84. The rest of these I'm using the older version. We have the function in there as 5x to the third power minus 3x squared minus 7x plus 4. Let 2 be the derivative of y1 such that x equals x, derivative with respect to x of y1 such that x equals x. You find that derivative once again under math, and then it should be the 8th one down. And then let y3 be your answer, 15x squared minus 6x minus 7, and check and make sure the tables for y2 and y3 are the same. Arrow over if you need to make sure you're looking at the tables for y2 and y3, not y1 and y2. And sure enough, they seem like they match up just fine. Now I went back to y1 and got my cursor over here on this little symbol on the left, hit enter once to make it into a dark, thicker line. And so then I play around with the graphs a little bit and experiment until I get a window that looks good. And the one I ended up with here was x going from negative 2 to 2, y going from negative 10 to 7, definitely not a square scale. And we graph this, and you can see the darker cubic polynomial for the original and the light, thinner polynomial, quadratic polynomial for the, or second degree polynomial for the derivative. Note a couple of things. The extrema of the function right here happens when the derivative is 0, and again the derivative is 0 here, this minimum. So both the local maximum and the local minimum happen when the derivative function is on the x-axis. When the derivative is at a minimum right here, if you could find that point, go straight above it here on the curve, and that's where you have an inflection point. Okay, let's continue on here. Alright, here's number 2. Number 2 is very similar. It's basically still just a sum of power functions, so it's pretty easy to do. 1/2 times 4 is 2. Then you take 1/2 minus 1. 1/2 minus 1 is 1/2 minus 2/2, which is negative 1/2. Negative 2 times negative 3/5 is positive 6/5. Negative 2 minus 1 makes negative 3 for the new exponent. Negative 2/3 times negative 7/3 is positive 14/9. Negative 2/3 minus 1 is negative 2/3 minus 3/3, which is negative 5/3. And e and pi are both constants. So e to the pi is a constant, and the derivative of a constant is 0. Again, we can check it by typing y1 is the original function. Now, I'm typing these in. Be sure, as you see here, to be sure to print or to put parentheses around the exponents. Okay, and I like to put parentheses around my fractions for the coefficients as well. Then again, y2 is numerical derivative of y1 with respect to x, comma x. It looks like this on the older system of a TI-84, older operating system. And then y3 is the answer we came up with, which you can see there. Be sure you notice the difference between a negative and a subtraction on your calculator keypad. And when I arrow over, I do table and look at the output there for y2 and y3, notice you get the same thing, so that checks our work. And here is a picture of the window, which actually I think those little squares or rectangle there is blocking out the 0 there, so it actually goes from 0 to 10 on the x and 0 to 40 on the y. And you can see the graph of the original function and the new one. Notice because of the x to the 1/2, this is only going to be defined for positive x's. And so we can see this. Actually, it looks like it turns out to be it looks like if you plug in 0, you get 0. So this particular one, f of 0 is 0. So, I'm sorry, f of 0 is e to the pi. So it starts at e to the pi, and then you can see it there going up. And the derivative there is undefined when x equals 0. It has a vertical asymptote. I'm sorry, f of 0 is undefined as well, because of these negative powers right here. So it's undefined at 0. Okay, so we have its graph coming up like this. Notice it's increasing on the original function, so the derivative is always positive. And it looks like we got concave down for the original, so the derivative is decreasing. Okay? Alright, on to number 3. Okay, go back here. Alright, 5 over x squared minus 7 square root of x plus 4 times the cube root of x squared. Well, in that form, it's kind of messy, but if we rewrite this using our properties of exponents, then we see that it's no harder than the last two. It's just a sum of power functions. So when we have 1 over x squared, that's x to the negative 2 power. So the first term is 5 times x to the negative 2 power. The square root of x, another way to write that, is x to the 1/2 power. So the second term is minus 7 times x to the 1/2 power. And x squared and then cube root is the same as raising x to the 2/3 power. So I'm using a couple of properties of exponents, and I'll just remind you what those basic properties are. Basically, we use the property that x to the minus n is 1 over x to the n, and we use the property that x to the m over n, if m over n is reduced, is the same thing as taking x to the m power and then taking the nth root of that. So those are the two properties of exponents that we used in rewriting this. Well, now that we've rewritten it as a sum of power functions, we can do it like the last problem. Okay, so negative 3 times negative 10, negative 2 times 5 is negative 10. And the power, you subtract 1 from it. Negative 2 minus 1 is negative 3. So here's our original f of x here. Take its derivative. 1/2 times negative 7 is negative 7/2. 1/2 minus 1 is negative 1/2. And then for the last term, we say 2/3 here times 4 is 8/3, and 2/3 minus 1 is negative 1/3. Now that's the correct derivative, but since the original problem had radicals in it, we're going to give it back in radical form for our final answer. And also it did not have any negative exponents. So I'm going to rewrite the first term as negative 10 over x cubed. Write the second term as minus 7 over 2 times the square root of x. X to the negative 1/2 becomes 1 over x to the 1/2, and then that x to the 1/2 in turn becomes the square root of x. So we get that for the middle term. And for the last term, we get 8 on the top, 3 on the bottom, and the x to the negative 1/3 becomes x to the 1/3 in the denominator, or the cube root of x for the denominator. So the final answer could be negative 10 over x cubed minus 7 over 2 times the square root of x plus 8 over 3 times the cube root of x. Now, some people like their denominators rationalized. That's no radicals in the denominator. If we go by that, which we don't necessarily have to, but if we do decide to go in that format, then we need to do a little bit more work with this. So on the middle term, we want to multiply the top and bottom of the fraction by square root of x. Notice in the bottom, then, you get the square root of x times the square root of x is just x, and but that puts the square root in the numerator. Similarly, we want to multiply the top and bottom by the cube root of x squared in the third term, so that whenever we multiply these together, we have the cube root of x times the cube root of x squared becomes the cube root of x cubed, which is just x. And so, if we want rationalized denominators, the final way we might write it would be negative 10 over x cubed minus 7 times the square root of x over 2x plus 8 times the cube root of x squared over 3x. Now, once again, we can check this. That black is what's that filling up? That's filling up a 5. So 5 over x squared minus 7 square root of x plus 4 times x to the power 2/3. Let y2 be the numerical derivative of y1. Let y3 be our answer, which I'm going to have to do part of it in probably some fraction exponents here, but do as much of it as I can, like I did that middle, like that first boxed answer there. Negative 10 over x to the power 3 minus 7 divided by parentheses 2 square root of x, close, parentheses, plus 8 times or 8 divided by, right here, 8 divided by, and then parentheses 3 times x to the power 1/3. So I did it that way. Check the table for y2 and y3. Looks like it's matching up. They're consistent. Picked a window from 0 to 10 on x and negative 10 to 10 on y. And the original function made it dark. And it is given by this graph here. Looks like for the most part it's decreasing. It's decreasing concave up, and it actually looks like it hits a minimum here and turns around, or somewhere it looks like this may actually hit the x-axis here. Okay, so the original may actually be concave up. It might actually be increasing in here. It looks like it. So the derivative may be slightly above the x-axis. Okay, let's look at the next example. Okay, in this one we have 3 to the x times 2x squared minus 4x minus 7. Well, the last step done in evaluating this function is to multiply the two parts. To multiply the 3x, the first part, times the 2x squared minus 4x minus 7, which is the second part, the second factor. So the last step is multiplication. We use the multiplication rule. In other words, the product rule. The last step is finding a product. We apply the product rule. So the derivative of x is then the first times the derivative of the second plus the second times the derivative of the first. So the first is 3x, then I take the derivative of the second plus the second times the derivative of the first. Notice I have a tendency to write this out very carefully this way. You might be able to do some of this in your head as you get better at this, but you absolutely cannot skip any of the steps that I'm doing. That doesn't necessarily mean you have to write every one down. Depends on how your teacher wants you to do that. But my experience is you're much better off writing it down than you are trying to do much in your head, especially at first. Now, later on, after you get more and more practice with this, like Cal 2 or Cal 3 students, we may want them to do a little bit more in their head. But at first, write everything out. So now we just bring down the 3x and the 2x squared minus 4x minus 7 that are right here. But we have to replace the derivatives here and here. Now the derivative of this part is, well, that's just a polynomial. We can do that one. 2 times 2 is 4. Power goes down to 1. And negative 4x, the derivative is going to be negative 4, and the derivative of negative 7 is 0. Over here, the derivative of 3 to the x is natural log of 3 times 3 to the x. Alright, well we have the derivative at this point, so that's a legitimate formula, but we would typically like to have our functions in factored form if we can. So what I'm going to do is notice that both this, here's a 3 to the x here that's multiplied, and a 3 to the x that's here that's multiplied. So I'm going to factor that out using the distributive property, which means I'm going to have two terms here. I'm going to divide each term by 3 to the x to get the things here. So this 3 to the x cancels, we're left with the 4x minus 4 for the first part. Plus, then this time the 3 to the x cancels, and we got a natural log of 3 times this quadratic here. 2x squared minus 4x minus 7. Now, I'm going to, this is just linear, even though the ln of 3 is in there. Ln of 3 is a constant. So let's get this the way we normally do our polynomials, with the coefficient times the power functions. So, we still got our 3 to the x out front. We got a parentheses here around the whole thing. To get the x squared terms, I'm going to distribute the ln of 3. So I get 2 times ln of 3 times my x squared. To get the x term, let's see here. The x term here has a 4x. Here has a negative 4 ln of 3x. So I factored out a negative 4. That left positive ln of 3 and then minus 1 times x. And then whatever's left is just a constant. I've got ln of 3 times negative 7, and then minus the 4 is the constant term within this part. So there's a quadratic here times 3 to the x. So again, we check that here in the calculator. 3 to the power x times 2x squared minus 4x minus 7 is y1. That's the original. y2 is the numerical derivative. y1, y3 is our answer. 3 to the power x, and then we have parentheses, open parentheses 2 ln of 3 times x squared minus 4 times parentheses ln of 3 minus 1, close parentheses times x plus open parentheses negative 7 ln of 3 subtract 4. And we check and we see that y2 and y3 have the same table. Again, don't forget to arrow over there. And then we can do the same, we can check our window here and experiment. To see this minimum down here, I needed to go pretty far down. So I got it, or at least got close to it here at y-min of negative 70. Y-max of 20 is what I chose from negative 5 to 5 on x's. And that gave us a nice looking little graph here for the original f, and then the derivative looks kind of like the original here for a while, but doesn't go as far down and comes on back up. So notice the derivative crosses the x-axis once, right around in here, somewhere between 2 and 3, I think. Let's see, yeah, the x marks are marked off by 1, so that's 2 and that's 3. So somewhere between 2 and 3 they cross, and that's going to be the derivative crosses the x-axis. And that's where the original function is going to have a local minimum. Actually, it looks like it's a global minimum as well. Then the derivative has a minimum as well, a little bit to the left of that. The derivative meets the minimum, and the x value right there looks like it's below that minimum, is going to be an inflection point for the original graph. We will come back in the next video and pick up the rest of the ones in this series.